Hi, I'm Curtis Skinner. I've been with Hypro Filtration about 9 years now. I'm a regional sales manager and have a little over 25 years of experience in the fluid power industry.
Hello there. My name is Richard Trent. I'm a regional sales manager for Hypro Filtration. Been with Hypro for a little over 16 years. Prior to that, about 20 years in the fluid power industry.
Hi, my name is Scott Howard. I've been at Hypro this is my 18th year. I was a strategic account manager, and this is the Hypro podcast. So today, what I'd like to ask is, let's talk about dirt. Other forms of this contamination we call solid particles, silica dust, basically just dirt. One of the top two contaminants that enters the system. Any thoughts on dirt, where it comes from? Where does dirt come from that gets into the system?
Primary ingression for dirt is probably breathers. Secondary would be unsealed reservoirs. Another place dirt gets into systems would be around failed wiper seals in hydraulic cylinders.
Okay, so we're talking about ingression is one of them, and air breathing, reservoir connections and seals, very important.
Well, we can't leave out anytime a system's open. So when systems are built, oftentimes they're not properly cleaned out, say reservoirs, that sort of thing. Anytime piping is added, you're introducing contaminant. Anytime you have any kind of opening of the system at all, if let's say a hose fails, pretty much anytime you open a system up for any reason, whether it's new construction, repair, upgrades, anything, will also introduce contaminant. Obviously, the primary source is what Richard talked about during normal functioning, things that are going on. But I think we need to kind of make sure we include that, because when you're looking at best practices or really talking to maintenance people or giving them ways that they can eliminate things, being able to prevent it is always going to be really important. So we need to make sure we include that too, I think.
On that note, since you brought it up, let's talk about the air breather. There is some discussion on what type of efficiency is required for the solid particles. Any thoughts on that as comparison to the oil filtration?
Typically, the type filter media that we produce to filter oil has a much higher efficiency when it comes to filtering air. I've seen reports anywhere from 1/12 to 1/4, and that depends on the actual active breathing of the breather itself. The greater the fluid exchange, the lower the ratio of particulate filtration. One way it would be 1/12, so a 12 micron filter would be filtering air at 1 micron. But if it's subject to a lot of fluid exchanges, then it would be a 4 micron filter would be down to around 1 micron.
So on particle sizes right there, just so we can cover that, generally speaking, we're looking at something underneath the 40 micron size we're not going to be able to see.
Correct.
So anything above that we can see, we know it's very large. So the particles we're really focusing on is stuff that we can't even see. It's going to look like a clear day, and yet there's particles in the air that are going to do damage to our system.
Correct.
So we need to have proper air breathing. Also, with the oil in a barrel, in a tote, air that comes in contact with that, it's going to gain dirt in the oil because oil is tacky, is sticky. What do we do whenever we add oil? Filtration as well. That's a pretty big deal. Would you consider that one of the most important aspects to keep dirt from getting into a system?
You know, you always hear the old saying, an ounce of prevention is worth a pound of cure. And I think that really is true in this situation. If you can keep dirt out, it's a lot easier than getting it out after the fact. So when you bring up a new oil and filtering it before it goes in, I think that's a good point where we kind of have to talk about a misconception that new oil is clean oil. So when you're talking about new oil, the definition of clean is going to vary by application. And oil suppliers don't necessarily know what their oil is going in. So they're not going to spend the money to get oil necessarily clean enough for your system. So the assumption has to be made, if you're not paying for a certified level of cleanliness, that it's dirty. And like I said, that's dirty is going to vary depending on what your system is. Dirty oil for a servo system is completely different than what you'd consider dirty for, say, a tractor that just has gear pumps and hand valves. So we have to assume, unless you're paying for a certain cleanliness oil, that it's going to be dirtier than what you need for your system. So absolutely. And the thing about filtering it before you put it in is you only have one chance. So you have to have really efficient filters.
Exactly. Good point. And one of the things that we like to harp on as far as adding oil to the system is to take that dirt out, because we want to provide oil to the system that's either as clean or cleaner, so we're not adding contamination to the system. Because then what happens when the dirt gets into the system and starts to go through the system? What are some of the things that dirt can do to a hydraulic or lubricating oil system?
We've got a coworker that uses the phrase, I guess he coined it, dirt makes dirt. But when particles leave a reservoir and go into the system, they're going to cause more particles to be generated, which causes an extra load on the existing filtration to try to keep you at a operating cleanliness code so that your components can survive.
Yeah, I mean, I always look at it like sandpaper. You know, if we have dirt in our oil, the thing you have to think about is you have to picture the inside of a system. So when oil's going through a system, whether it's a lubricating system or a hydraulic system, which are the two we're pretty much dealing with, some fuel systems, we're forcing this fluid through really tight areas under high pressures. And to me, the way I can visualize that is like sandpaper. We're pushing sandpaper really hard. So the finer the sandpaper, the less material you remove. The less particulate you have in that oil, which is going to be abrasive, the finer it is, the less you're going to be removing. Conversely, the more particulate you have, the more abrasive you have in there, the more material you're removing. And that goes to what you're saying as far as dirt makes dirt, because we're removing material with this abrasive and we're just continually generating contamination. So the cleaner we can get it, the less we're generating internally.
And really what we're talking about in systems is not necessarily the large particles, because we feel like that's going to be easy to filter. And it may not be the submicron particles, because they can fit through those clearances. So what we're talking about is the clearance size particle. And that's very important. And so in a system, I'm going to use a question that I hear often to ask this question is, how do we determine what the clearance size particle or the ISO codes is? The question I hear often, I'm sure you both as well, is, or I have somebody say, I need a 10 micron filter. What do you say whenever you hear that? Because we want to direct the conversation towards monitoring and mitigating and controlling the clearance size particles in that system. What do you say when somebody tells you that? Curtis, I need a 10 micron filter.
Usually when you hear something like that, that's an opportunity to kind of step back and help somebody understand what they're really asking for. So when somebody says I need a 10 micron filter, they really need to understand what they're trying to accomplish. So you have to start talking about, okay, all right, well, we have 10 micron filters. Why do you need that? So let's start talking about your system. And what I always do is I talk about the most sensitive component in the system. So first of all, 10 micron can mean a lot of things. There are various different sufficiencies of a 10 micron. A 10 micron cellulose filter might catch 1 out of every 2 10 micron particles that come up to it. It's 50% efficient. Or a 10 micron filter could be one that's a beta 4000. So for every 4,000 particles that come up to it, 1 gets through. So first of all, the idea of 10 micron, you kind of need to help somebody understand that doesn't necessarily mean much, but it gives you an opportunity to start talking to them about their system. And you need to zero in on, all right, what's the most sensitive component in your system? Because the most sensitive component in the system is going to drive everything else. And it's going to have the tolerances that we're going to work with. So if we can look at, like when I talk about the most sensitive one, it's the one with the finest tolerances. If I can get the oil clean enough for that, I know it's going to be clean enough for everything else. So that's usually a starting point of a conversation. They're at least thinking about filtration, wanting to get their oil cleaner. They know they need to do something. But it's just a beginning. It's just a place to start. It's usually a good place where you can start an education process and you can start asking some questions. But just that question alone tells me essentially nothing. If somebody says I need a 10 micron filter, they just know they need a filter, and it's a starting point for a conversation.
Yeah, I think that's a really great point. I want to get Richard's take too, but basically what I'm hearing is we don't just take their word for it and just quote them a 10 micron filter. We start prying, basically. What do you do?
Usually I laugh,
All right.
mainly in homage to a ex-coworker of ours, because on a call with him years ago when a statement like that was made, he said his socks are a 10 micron filter. So if you think about it, anything that has fibers in it could capture almost any size particle. It may only capture, as Curtis was mentioning a while ago, 1 out of 50. It could capture 3,000 out of 3,001. So since most any fiber can remove some quantity of any particle size, the conversation really needs to be, how clean is my fluid? But more importantly, on what Curtis was saying, how clean does the oil need to be in order for the components within that system to achieve their design life? And one thing that struck me as interesting years ago, I was trying to figure out what the design life was for a hydraulic piston pump. And in a conversation with one of the smartest fluid power engineers I ever knew, he told me that all of these life calculations on hydraulic components are bearing L10 life calculations. And if you think about it, hydraulic components are nothing more than bearing fits. Regardless of what the component is, whether it's a piston pump, a hydraulic cylinder, everything is a bearing fit. And then you start thinking about how clean does the fluid need to be so that, as Curtis was mentioning earlier, we don't get enough particles in between those clearance fits to cause abrasion, which then leads to greater clearances, and then from there you get higher inefficiencies of the hydraulic components, and it typically manifests itself in heat and premature failures.
You're definitely taking that conversation away from that 10 micron statement and starting to pry and ask questions, because it ultimately, like you both said, we have an ISO code limit that the system should operate under. And we call it a limit, not a target, because a target is something to achieve and a limit is something to avoid. So it's a limit. We have to determine what that limit is. And then when we determine what that limit is, like you said, based on the most limiting component, then we need to determine what efficiency media is required. And just looking at media grades doesn't tell the full picture. The operating conditions of the system are a factor as well, like ingression rate and other factors like that. So just a 10 micron filter it's an invitation, if you ask me, to start a conversation.
I agree.
Some companies, I'm going to just kind of jump around and talk about a few of the things with as far as particles are concerned. Some companies used to show only 2 ISO codes, and we'll talk about ISO codes probably in a little bit more detail in another podcast. But we do have 3 ISO codes, and what we're talking about basically is the most limiting of those 3, the 4, 6, and 14 will be the 4 micron ISO code. As far as that is concerned, some companies show 2 ISO codes. Any thoughts on that? Any opinion? We see that less and less now?
I do. I mean, my understanding of the genesis of the ISO cleanliness code was that what we now recognize as the 6 sub-C channel and the 14 sub-C channel, back when the ISO code was first adopted, it was 5 and 15 microns. The reason that those were chosen, again from my understanding, is that they determined that a 15 micron particle was a good indication of system wear, and a 5 micron particle was a good indication of silt. But with the advance in hydraulics to electro-hydraulic controls, I think it was Vickers many years ago advocated successfully for the inclusion of what back then, pre-1999, was known as the 2 micron channel. So at that moment in time, we went from a 2-digit ISO code to a 3-digit ISO code. And again, y'all can check me on this if you want to research it. I think that happened in 1986. Somewhere around that time frame. And then, of course, in 1999 to 2000 time frame, the standards were changed, and we now look at 4 sub C, 6 sub C, and 14 sub C. So the companies using just the 2-digit code are essentially ignoring the fines or the small particles that definitely have to be accounted for if you get into electrohydraulics.
I think anymore you generally see that in mobile applications. I mean, there are some old systems where somebody's looking at an old reference, but I think it's usually in like mobile applications where they have higher tolerances, like say gear pumps and the hand valves I was talking about before. I think it's really going away in industrial settings.
Yeah.
Yep.
Some diesel engine manufacturers may still just look at the 6 and the 14.
And with those, it makes sense because their tolerances are so much higher.
Right.
So,
As far as hydraulics is concerned, lubricating oval systems, rolling element bearings, journal bearings, very tight clearances. Yes, so that third, what Vickers introduced a long time ago, I believe is a very important one. Has to do with more of the clearance size particles, but also includes the larger ones. So when I look at a lab report or a test report, first thing I like to do is look at the 4-micron channel. Kind of gives me some information. Love it that. What if a customer says to you, my ISO codes are only 1 code above the limit. I'm close, so I'm good. How do you respond whenever you hear that? Because we hear that a lot.
That one code difference could be 1 particle or a fraction of a particle if you're at the upper limit of the range of 4406. But it could be as many as 50%, or excuse me, twice as many particles. I said that incorrectly.
that actually kind of dovetails into something I think that is important to include. I had a hard time when we first started talking about limits and we set them lower than what manufacturers recommended. And this kind of goes to that. When you take that reading, that's usually taken when everything's going well. The system's closed. You haven't just done some maintenance on it. You haven't opened it up for some reason. And saying you're only one code higher, we know from years and years of test data, any event that happens, that code's going to jump 2 or 3. And a quick understanding of codes, to your point, each time you go up a code, you're essentially doubling. We need to have a realization that we want to stay at or below what the manufacturer recommends for maximum life. In order to do that, we have to understand that there are events that can happen, that happen regularly, like opening up a system to add some oil, changing a filter, repairing a cylinder. Those codes and those limits start becoming really important, that we need to look at where we need to be during normal systems to give us a little bit of cushion.
I like to call that an insurance policy.
Yeah, and it's a kind of a universal thing. Like when you're driving your car, there's a reason you don't tailgate. You want a little room for when things happen. If everything's going right and the person in front of you is stopping slowly and there's no deer running across the road and there's nothing happening, you're fine tailgate all day long. But that's not how life works, and that's not how the life of a system works. Things happen, and you need to give yourself the insurance policy or cushion. You need to have some room. So I'm just one code higher means that I will never be where I need to be, and I'm often going to be much higher and much dirtier than I should be, which translates into your system's not going to last as long. So all this equipment that you've spent money on, all these things you've done, you're not getting a return on your investment, because the choices you're making there, allowing it to be one code higher and thinking that's okay, you're shortening the life. You're throwing your investment away. So that's kind of, I think, how we have to look at it and how we have to explain it, that you need some room for when things go wrong.
I think that's a fantastic analogy with the tailgating too, because that really puts us in a practical application so people can understand what you're getting at. That's very, very good visual, because that's real. You're going to be taking your ISO codes during normal operating conditions, and then an upset occurs. Particle counts aren't going down. They're going up. So I think that's a really good point. Another thing I'd like to talk about is what you mentioned a few minutes ago, is how we recommend a little bit lower ISO code, and I'd like to hit on that because I've had customers claim to me, well, you're just trying to sell more filters, I mean, that's what a filter manufacturer does. The reality is, we go back to Stephen Pearson's analysis on, or analogy on dirt makes dirt, and he likes to use the rubbing your hands together with and without sand in between your hands, and you know if you have sand between your hands, you're going to get more skin cells come off. So dirt makes dirt. If you maintain ISO codes significantly lower, then there's less dirt in the system to make more dirt. So filters last longer. And remember one thing that we have to recognize about all filters. You're either taking more dirt out than ingression coming in and being generated, or you're taking less. You're either lowering your ISO codes or it's eventually going back up. So I think it's important that when people see what we're talking about there is twofold. Like Curtis, like what you said, we want to be low enough to where when an upset occurs, we're still below that limit. But also, you are going to use less filters if you can maintain that. Any thoughts on that?
That's one of the most counterintuitive things that we have to explain to people, is that by allowing your system to operate at a higher ISO cleanliness code or a higher particle count, there's more particles leaving the reservoir, so therefore there's more particles coming back from the system into the reservoir, which means there's more stuff to be removed. When you use tighter filters, or when you get filtration in your system so that your ISO cleanliness code is running really low, there's fewer particles generated, therefore there's less particles to be removed. And in way too many case studies, I've demonstrated for customers that cleaner fluid results in longer element life and a lower cost of filtration, not even accounting for the increase in component life.
There is one caveat. It's the filter that's maintaining that low ISO code as well, plus the system being sealed up. So you can't get to a low ISO code and then throw any filter in there and keep it there. It has to be a high quality filter element to be able to pull more contaminant out that's being ingressed and generated. But at that point in time, now you're in a really good situation. It's very difficult to explain to the customers. Maintaining lower ISO codes is less filtration, but it is true.
And that's one of the reasons we do so much testing with customers. It's not, hey, trust me on this. It's give me the opportunity and we'll prove it. And generally, when given the chance and we successfully prove that fact, then we gain a customer for the duration moving forward.
So we've been talking about solid contamination testing, performance. Filters have to be tested so we know what the performance is, lab versus real world. Would you like to talk about that?
Well, Richard mentioned that we do a lot of testing at customer sites, and we're actually testing our filters in their machines. And I think that really brings up a good point, because we can test stuff in a lab all day long. We can test stuff on a different machine all day long, and we don't know how it's going to perform in your machine. We can have a pretty good idea, but the reason we do so much testing in the field at customers to show them the results they can get is because every machine is different, every application is different, and the real world is significantly different than a lab.
Most definitely. And most of the lab tests are performed using a mil-spec fluid that's relatively thin, 15 centistokes. It's done in a very controlled environment, so you can manage a lot of variables. So all of these various tests that are done in labs are important. They're important to help develop filter media and filter construction. But if I'm concerned about the reliability of a lubrication system or a hydraulic system, and I'm worried about my 3-digit cleanliness code, I want to know how filters are going to perform in my system, at my plant, in my environment, because all of those things change from not just plant to plant, industry to industry. You can go to 3 sites that have the same exact piece of equipment, but because of the surrounding environment and the severity or lack of severity of operating conditions, you're in different worlds. So,
well, it comes down to what we always talk about: how clean is my oil, and how long are my filters going to last?
That was bottom line. 2 questions right there. Yeah. So before we get to the real world, let's take a second to talk about the lab side, because I think we really do a lot for our customers in the lab. And I'd like to talk about that. So let's go step one, ISO 16889, what everybody does. And then from there, steady state testing. Any thoughts on that procedure?
Well, I think the thing about 16889 is the one thing people have to understand with a test protocol like that. The idea isn't directly tied to quality or performance.
Right.
It's the main purpose of a test protocol like that is consistency. So what I mean when I say that is we need to know that if I have a filter and I test it, and whether I test it in Anderson, Indiana at High Pro Filtration, or I test it, okay, I don't know where anybody else's plant is, but if I test it in Italy, I test it in South America, anywhere. If I test that filter, I need to know that I'm going to get the same results for the same filter. So the first thing you have to understand about any test protocol is it has to be able to be repeatable and consistent. Yeah. Now that's a good thing, and it's a really good starting point when you're talking about a filter, but that doesn't necessarily translate to the real world. So let's look at 16889. The thing about 16889 is, one, it is very repeatable, and you can get very consistent results. So that's a good thing. There are some problems with it, and Richard talked about one. It's an unrealistic fluid. A mil-spec fluid that's 15 centistokes is very dissimilar, very different from an ISO 320 gear oil when it's 50 degrees outside. So that's the first thing is it's the thin oil. The second thing is when that test was being developed, it wasn't really practical to add any variability. So if you add variability, it makes it harder to make it repeatable.
Exactly.
So that test is conducted at a steady state. So with steady state, it means you have a consistent flow across a filter. Now that will give you an important piece of information. That will give you the piece of information that tells you how efficiently that filter can capture certain particle sizes. That's good. That's a good piece of information. What it doesn't tell you is what happens if you turn the machine off or you turn it back on. It doesn't tell you what would happen if you vary the flow. So it's giving you a picture of an efficiency in an idealized world where you have a set temperature, you have a set viscosity, you have a set flow. It's a very easy situation for a filter. So just a quick, if we're looking at this test, just so we make sure we understand it, steady flow. It's taking readings on a fairly stretched out basis, and it just kind of gives you a picture as you steadily, consistently load a filter at the efficiency of it. It's not necessarily a bad thing, but it doesn't give you a lot of information. It pretty much just shows you capture efficiency. So when you look at that test compared to the direction the industry is looking at going, which is we were talking about earlier, the 23369, that adds in another variable. The thing we always talk about with filters, or at least I do, is a filter's not a black hole, right? So just because a filter caught a particle doesn't mean it's out of your system. Until you change that filter, it's still in your system. So the 23369 adds the variability of flow by changing the flow. And once you start changing the flow, then you start putting stresses on a filter that are going to make it more similar to the real world. So, Richard, you were talking about real world testing. They add that dimension by varying the flow. So now we're looking at another part of the equation. Capture efficiency is all we looked at with 16889. It doesn't really tell you anything else. There are some people that will extrapolate out some dirt holding capacity, and you can do that, but once again, that's in an idealized setting. But it doesn't tell you about retention. So now with 23369, Now you're looking at retention because you're varying the flow.
Yeah, I think 23369, if it actually comes to be, will be a more accurate test. It would be a little bit more accurate to what you're going to see in the real world. But again, all of these lab-based tests, 23369, 16889 as well, they use medium test dust as a rule. Medium, that's the contaminant that is injected into the system. And that particular contaminant is ISO certified for a specific distribution of particles per volume of fluid that goes into the test stand. And again, that's great for the lab. That's great for media and filter development.
For consistency.
For consistency. But it's not real world, because that's not what an industrial hydraulic system in a sawmill would see, as opposed to a hydraulic system on a bulldozer in a surface mine. The distribution of the particles that are challenging the system and the filters are entirely different. So therefore, you're never going to see in the real world results that you see off 16889. And too many times in my 16, 17 year career at Hypro now, I've done particle counts with filters that have the same beta ratio, and that's one of the data points that 16889 develops. That's where the beta ratio of a filter is developed. 3 filters by 3 manufacturers with the same beta ratio, and you do downstream particle counts of those 3 filters in parallel, and you get entirely different ISO cleanliness codes. And at the end of the day, back to a conversation we had a little bit earlier about, a quote unquote 10 micron filter, I'm more concerned with, is my oil clean enough so that I get good life out of my components, so I'm not having premature failures? Can I maintain that cleanliness code economically, because you have to be able to maintain it economically. So I'm more concerned with how will any particular filter perform in my system, and what is it going to cost me to operate my system using that filter over a long period of time.
Basically what I'm hearing is the lab testing is one thing, but you want to confirm it in the system because each system is different. The particle distribution can be different from the lab setting, which I completely agree is needed. If I own the equipment, I would do the same thing. I want to test it on my system to see what it's going to do.
Now, I will say, though, I hope that 23369 gets passed, because it does give you a much more realistic picture of how a filter is going to perform. When you start introducing the variable, and just in case there's some confusion about, we keep throwing these around, 16889, 23369. So the proposed test protocol, the ISO proposed test protocol, which I think it's in committee at this point, I'm not sure. The biggest difference between it and 16889 is it's going to vary the flow. So during the testing, instead of having a steady flow, you're going to have 2 flow ranges, and it's a 4 times factor. So it's going to be going up and down, and it has a very sharp change in the flow rate. So it goes from low flow, abrupt change, high flow, abrupt change, low flow, which does get closer to what we see in the real world. And people might say, well, I have a lubrication system, or I have an offline system. I don't have that. I have steady state. Well, if you never ever turn that system off, then yes, you do. If you ever turn it off and back on with a dirty filter in it, you just introduced that variability. What I do like about that is you're now introducing shock. So you're compressing media when you increase flow, and you're relaxing media when you decrease flow. The limitation that I see on these tests is, although they're not realistic, they're not, like you said, they're not realistic. The limitation is, to me now, when I'm looking at it, is the data you get. So when we look at those tests, the way the particle counts are done, you might know, this filter performs better. So you're doing 23369, you're stressing a filter, you're changing these flows. You may know, yes, a filter performs better, but you don't know why. And to me, that's the brilliance of the DFE. With our test, with the DFE, even though we're not doing as abrupt a change of the flow rates, we have a really powerful development tool, which enables us to build a filter that's going to perform better in the real world. And what I'm getting at there is we take counts way more often on the DFE. And we're looking at how our filter performs at low flow, but we're also catching how it performs when we transition, because we're taking so many more counts. We don't transition as hard, but we are able to count particles, and we can look at the efficiency at low flow, transition from low to high, high flow, and transition from high to low. The really interesting thing that we've seen with the testing we've done so far, because of the data that we're getting with DFE, we're able to see where a filter performs well and where it performs poorly. Well, why does that matter? Well, let's say you have a filter and it's giving you mediocre performance and you're not really sure why. Well, with our test, we know why. It could be that this filter does great at low flow. Man, it's a dirt hog. It's catching, it's holding on to things. It does great when you hit it a little bit. You go from low to high and you compress everything. It holds on great. It performs great at high flow. But as soon as that flow drops and the media relaxes, it lets dirt go. The neat thing about the way we do it, and it's a lot harder to do, and there's been a tremendous amount of development that had to go into our test stand, we know where we perform well and where we perform poorly, and we're able to develop a better filter that we then put out in the field and make sure that it performs well. And what's interesting is we've had some filters that you can develop a filter that looks fantastic on a variable flow test. You're doing all these things. We're doing the cold start, and you put it in the real world and it doesn't perform well. So without that, you're not going to get a good filter. But what I think is really telling is we get better data, and when we test on the 23369, we perform way better. When we test in the real world, we perform way better. But DFE as a tool has given us that because of the data that we have that you'll never get from the other tests. The other tests, you get what's considered normalized data. You have all these things going on, and then you take a count. And you have all these things going on, and then you take a count. Whereas we're taking a lot of counts and watching what goes on.
That's exactly right. And there's several questions that have generated from this conversation that I'd like to go over that's important. And you hit on something that's really, really important for us to recognize is we are trying to break down our test in the only 4 situations your oil will be subjected to in the system, but all 4 of them individually. Low flow, steady state, transition to higher flow, steady state, transition to lower. There is no other scenario that the oil can be subjected to. So we are breaking that apart. So we can see where we need to increase our efficiency or performance of our filter element. Let me take a step back and talk about dirt holding capacity. One of the fallacies of 16889 is other companies like to use dirt holding capacity in that test as a marketing tool. What do you say to that? Whenever a customer says, look what customer or competitor X is showing as far as dirt holding capacity, how do you approach that?
Dirt holding capacity technically should be written as apparent dirt holding capacity. There should be a letter A in front of the DHC. And for the most part, plain and simple, dirt holding capacity is the amount of contaminant in grams, this MTD, medium test dust we mentioned earlier. It's the amount of that in grams that was injected into the flow stream during 16889 until the element reaches terminal pressure drop. The problems with a lot of these lab-based tests, especially with dirt holding capacity, number one, the person conducting the test chooses what terminal pressure drop is, or the differential pressure reading at which the test ends. It stands to reason that the greater the differential pressure for terminal pressure or end of test, the more dirt's going to be injected. So therefore, the higher dirt holding capacity we can publish in our literature. That's one of my biggest pet peeves with 16889 and the way that value is I guess marketed would be the right word.
I would say that we have to use the operating conditions to establish that if you're going to list an ADHC.
Well, if terminal pressure drop, and in most cases terminal pressure drop is somewhere around 50 PSID or 60 PSID. But when you start looking at most filters that used in industry, their bypasses or their indication to change the elements are much lower than that. So we publish data. I say we, that this industry publishes data of dirt holding capacity. If you want dirt holding capacity from us, from HiPro on a filter, we're going to ask you a whole lot of questions before we give you a number. Things like at what differential pressure, and at what viscosity, and at what ISO cleanliness level.
What flow rate?
The flow rate. All of these things matter because they impact dirt holding capacity, or they impact filter element life, which essentially is dirt holding capacity.
Well, you hit the one big factor, which is terminal pressure drop, which is huge, and you hit the other point, flow rate. So when you're looking at a filter, you've got a certain amount of surface area, and the flow rate is, you start looking at velocities through the filter. So one way to make a filter hold a lot of dirt is to turn the flow rate down. And it doesn't take a lot to visualize if you've got this flow stream coming through, it's really fast, and it's got dirt particles and this filter's catching it. They're stacking up and they can't fit into different places. They're just layering it. You slow it down, they can kind of work their way in.
Well, it's harder to catch and hang on to a fastball than it is a softball or a slow pitch ball.
That's a good point. In most cases, though, our customer may not be interested or may not be able to change the flow rate. So what do we do next?
Well, I guess what I'm getting at there is when you're looking at dirt holding capacity and you're explaining to somebody, you need to explain that that is a variable that's not fixed in a test protocol, and that it's an easily manipulated value from testing. To your point, it ends up becoming just a marketing gimmick.
Absolutely. Yeah.
So it's like the 10 micron question. I need a 10 micron filter. Well, when somebody asks you about dirt holding capacity, it's actually a really nice opportunity to educate somebody on what's going on with a filter and how filters work, and help them move to how clean is my oil and how long do my filters last.
I look forward to that question. I agree with you.
Yeah. So what's the dirt holding capacity of my filter? There's a whole lot of variables, but here's what I know. The cleaner your oil is, the longer that filter is going to last. And dirt holding capacity is less of a factor if we get that oil clean. So do our filters hold a lot of dirt compared to the competition? Absolutely. Is it the thing I should be most worried about? No. What you should be most worried about is, in your system, are we able to get you to a cleanliness level that you need to be with an economical life on the filters? So that question is a good starting point again. But let's talk about what's really going on in the system. We want to get the oil as clean as it needs to be, and that will extend the life of the filters.
I like to use the phrase, the Tetris Effect that we've talked about to explain to people who don't know contamination control like we do, to kind of bring them into what you're talking about as far as velocity changes. You're exactly right that the higher the velocity going through the element, your particles are caking on top of each other, face loading on the outside. We have a depth to our media, and I'm not talking about pleating. There's a thickness, like a sheet of paper. There's a thickness to the sheet of paper. There's a thickness to the media. That's our capacity. But the velocity can cause that capacity to go down if it's too high because we're face loading, we're caking. So I like to use the term the Tetris Effect because a lot of people nowadays have played the game. Consider level 3 versus level 10, just throwing out two levels. It's a lot more difficult for us to clear out those rows in that Tetris game, but if you think about particles going through a filter, you know, my fingers, that's what a filter looks like. When your dirt is coming through, it's more coarse and then more finer. Well, if it's a real high velocity, we're face loading, caking on the outside. If I put my filter element in a system where there's a competitive filter that has maybe a not as efficient, but it's a lower starting delta P, there's a good possibility our first filter element, as it cleans up the system, doesn't last as long. It introduces us into this, or gives us this chance to talk about dirt holding capacity. And what I like to tell customers is it's the window. Your window there is from where you start to where you end is going to affect your dirt holding capacity. And the lab testing isn't that window for your system. We're going from 0 to 60 psid. And because 16889 lets us pick that steady state, there are competitors out there that can choose to pick a lower flow rate to increase that dirt holding capacity for marketing. It's just a lab test. So that's what I like to tell customers is your window for how long your filter can stay in that system from starting DP to terminal is a major factor in your dirt holding capacity as well. So if you have a filter that's expiring like you talked about, and we can't change the pump flow rate, what can we do? We can upsize the filter housing. What's the first thing a customer says? Well, you're just trying to sell filters. But in reality, when we do that math, there's a big difference. If we double a filter, what happens to our capacity?
It increases by a factor of 3 to 5x.
Why is that?
Because the flow density decreases.
And you give your particles more of a chance to organize in the thickness. This is real. This is what we're talking about. So then we got to take it to the real world. What do you do whenever you want to set up a test? What are some things that you'd like to cover with your customer to make sure that this test is unbiased, but we're going to get real results that are, the data is trendable and actionable?
In a perfect world, you would have a sample port on both sides of the filter. So you could do online particle counts both upstream and downstream. And you would do that multiple times prior to an element change so that you have a good understanding of what the equilibrium and cleanliness level is of the system, and you see a measure of the existing filtration's single pass efficiency. You got a 3-digit ISO code coming in. Once the ISO code coming out, there's your single pass efficiency, and you go through a life of that filter. One of the things you mentioned just a moment ago is putting a set of filters in and they not lasting as long as an incumbent filter is.
Yeah, initially, exactly.
So if that's all you're doing, okay, I'm going to try this filter. My current filters are lasting a week, and I put this filter in and it lasts 4 days. Oh, that filter is no good. I can't use it. I can't afford it. If you don't know what your particle counts were, that's a missing link of data.
The conversation's over at that
So
point.
if you do in fact change filters, and you see what I expect to see when we put our elements in the system, initially the downstream particle count will decrease because our elements are more efficient. You can show that to your customer. Over a short period of time, the upstream particle counts will begin to decrease because your filter is cleaning up the system. Shortly after the upstream particle count decreases, the downstream particle count will decrease again. So it's really important if you're going to do an accurate test to sample on both sides of the filter, keep up with differential pressures, keep up with cleanliness levels or your ISO cleanliness code or the hard raw particle count data on both sides of that filter, and then keep up with the actual number of days in service, number of weeks in service. Typically a test, the majority of the tests that I've conducted can go on for anywhere from 3 to 6 months. That's a lot of trips into a plant. It's a lot of time spent with a particle counter. But at the end of that, you have given the customer enough information to make an informed decision, as opposed to, hey, here's a PDF file on the internet and here's a quote. Again, it's really important to me in this job, and it would be important to me if I was on the purchasing side of filter elements, to actually see, how does this filter perform in my system? How clean is my fluid? How long does that filter last? Because I want to know my cost of ownership, not my cost of one filter element.
That's a good point right there. The cost of ownership. A filter is not a good place to save money. So
I like your analogy. Can you go over that,
Yeah,
Curtis? It's a
so-
really good one.
when you're trying to save money on filters, you're trying to save money on the least expensive component in a system with the most important job of protecting the most expensive component in the system. And one thing that's really important, and I that's my simple way of remembering that, but one thing that's really important is instead of saving money on filters, you can save much more money with filters. And that's the distinction right there.
Right.
Now, we have a competitive price product. We're never going to come in and be way higher than somebody else, but trying to save money with your filters is a pretty bad idea, because there's always going to be somebody who's going to make a cheaper filter. This is real savings that you're talking about. You were talking about those bearing life extensions and the
Correct.
different calculations. If you can get oil cleaner and spend a similar amount on your filters, you start getting into tremendous cost savings because you're extending the life of equipment. What happens when you extend the life of equipment? Well, you're buying, let's say, pumps. You're buying fewer pumps. You have less time replacing those pumps. And while replacing those, you have less downtime. That is real cost savings. That is where cost savings is, and that's where you need to live. If you're a maintenance professional, if you're somebody in reliability, even if you're in purchasing and you're tasked with saving money by spending a few pennies less or a few dollars less on your filters and saying, look at all these cost savings, but you bought 6 more pumps, you didn't save money. You had more downtime. You didn't save money. You were penalized by your customer where you have a just-in-time contract because you had downtime and you failed to deliver. You didn't save money. This is where people can save money, and this is what actually makes filtration, which on the outside doesn't seem real exciting, makes it really exciting, because we're improving the world that somebody's working in. We're making their pumps last longer. We're letting their maintenance people, we're giving them the ability to work on things they planned on doing instead of having to replace pumps because they keep breaking down. That's the conversation that matters. That's why we do that testing. We are drastically lowering people's costs of operation every time we lower those ISO codes. And that's where the conversation should be.
Correct.
So how long does the filter last, and how clean is my system? When you have a customer ask you to quote on a filter for their system, and we haven't seen the system before, there are some potential pitfalls before we can just give them a competitive price. What are some of the things you're going to ask them whenever we go down the road of quoting our filter in the system where it's not currently? And I'm really getting to is we need to confirm sizing, obviously.
Right. Well, you need to know flow rates.
Flow rates.
You need to know the fluid that is being filtered. You need to know at what temperature that fluid is being filtered. You need to know what components are within the system, because those components will determine how clean the fluid really needs to be. And that's definitely the starting point. If you just go part number to part number, you can do a comparison, but you're not comparing everything. You're just, at that point in time, you're just comparing a price.
You know, one of the industries we've looked at, and I'm sure it's true in others, when you start looking at filtration on equipment, it's generally not the most important spec when somebody's ordering a new machine for their plant, right? So you're ordering a machine, they're looking at different factors, like 1, what's the machine cost? 2, how big is it? 3, how many parts can it produce? All these different factors. Filtration's usually not the primary concern. So one of the realities that we deal with when we go in and you're talking about being asked to cross a filter and getting these parameters is oftentimes it's undersized, or it's an afterthought, or it's not sufficient for what they really need anyway. So we're already on the ragged edge of performance, and now you're looking at changing something, and that's where those factors become so important.
Right.
Because the last thing you want to do is put something in that's going to cause you to go in the wrong direction. It's not going to last as long or something like that. So if they're going from an inefficient filter, one of the nice things about inefficient filters is you can flow a lot of oil through them. So yeah, that's great. When you're sizing it for a piece of equipment, you can put a smaller filter on. There's less there, so it costs less to build that machine. Well, the owner of that machine has a different set of priorities. Now they want to keep that machine running. They have things that they want to do. So it's really important to get that information. If you're going to size a filter and we're just replacing elements, those questions, you have to ask those questions, because we know that it wasn't a priority when they built the machine, and it's quite likely undersized.
Well, the reason I bring that up as well is we're talking about testing. Are either one of you going to walk into a system and just say agree to testing without doing any of this research? No. Because we need to know what we are getting into, because we know that it's going to be immediately we're going to start teaching the customer more about their system. But to get into a competitive test, we need to know all this up front. And very common, we'll see a filter that's undersized. Let's say we come across that. What do you say to your customer when you have an undersized filter? They're going through it a lot. They think that the filter doesn't have a lot of capacity, but we look at the numbers and we recognize immediately it's undersized. How do you approach that with a customer?
Well, in testing, you can actually show them that.
Right.
Some of the conversations is starting clean pressure drop versus the end of life of that particular filter in that particular system. If you've got a filter that indicates dirty, that it needs to be changed at 20 psid, for example, and your clean pressure drop, the pressure drop when a brand new element is put into that assembly and the system is up to operating temperature, normal operating conditions, if that clean pressure drop is 15, you only have 5 psid of differential pressure to consume for filtration. Where if the clean pressure drop is 5, that gives you 15 psi of differential for filtration. So the greater the distance from clean pressure drop to end of life pressure drop, the longer a filter will last. If it is undersized, then you look at offline filtration. Even in that scenario, though, I've been able, in some occasions, with an undersized filter, to still achieve everything the customer wants to achieve, and at the same time decrease his cost of ownership.
So in that scenario, let's go down that road. Your customer is not able to change the filter housing size that's in line, but we know that we can accomplish this maintaining the ISO codes under the limit other ways. What are some things that you would mention to this customer? You said kidney loop. I'm a big fan of kidney loops.
Offline filtration is one of the easiest ways if you do not have enough capacity for the proper media online in your system.
Well, there's other things you can do too. I mean, yeah, we sell filters, but Richard made a reference to something one of our coworkers once said about his sock being a 10 micron filter. Same guy also said, I don't sell filters, I sell clean oil. So what does that mean? Well, if you're at a customer and you're looking at their equipment, you're doing them a disservice if you're not telling them about the other things that they can do to get their oil cleaner that have nothing to do with our filters.
Right.
You talked earlier, we were talking about points of ingression. If you walk in and have a hydraulic cylinder and you see oil dripping off of that cylinder, well, they're pumping dirt into that system. And you need to tell them that. There are things that they can do, housekeeping things, maintenance things that they can do that are going to get them cleaner oil before they ever start touching the filters. So good breathers, fixing leaks, just best practices. There was a test that was done before my time where when the customer was changing filters, we were doing filter monitoring. When they changed filters, there was this huge jump in particle counts, and it was simply a matter of cleaning the area around the element before they changed it so they didn't get dirt in. There's an excellent opportunity when you're in a plant and you're looking at something for a test or evaluation or whatever to be able to show the customer other things they can do. I was asked to do a test one time at a steel mill, and I was doing that survey. I was doing my walkthrough, looking at the filters, looking at the machine. And on the reservoir was a 12-inch by 12-inch opening. There wasn't a cover even laying anywhere. Well, we're talking about particles that are 4 microns. We talked about, I think, a young person, not me, we all have our readers that we have to wear, can see 40 microns and can't see any smaller. And they had a 12-inch by 12-inch opening in a dirty steel mill. Well, putting a better filter in is not going to do much. Let's close that hole, and we can start progressing from there. So there's always that opportunity where you can show somebody really nice cost savings and things they can do with some best practices they need to be doing anyway. Let's close it up. Let's fix leaks. Let's make sure that we're not letting stuff in that we don't need to let in. And then our filters are going to last longer. Everything's going to last longer.
I read a study years ago, and I cannot remember the publication in which I read it, but and it goes back to your ounce of pain and a pound of prevention statement from earlier today. For every dollar that you would spend keeping a particle out of your system, it will cost you $10 to remove it once it's there.
I saw a recent report that updated that to 100 now. Interesting, but it's at least 10. But I saw a recent report within the last 5 years that actually it makes a case that for every dollar that you spend on the front side, if you don't, it's now going to cost you 100. It's pretty substantial. And what we're saying basically is what? It's going to take a lot longer to pull that dirt out.
Right.
Once you let it in the system.
So fix your leaks, seal your reservoirs, take care of your breathers. Don't use the chrome bayonet style filler breather cap that's got the carbon steel 40 micron Brillo pad in it that, I don't know, eventually it's going to just turn into rust and be completely gone. But again, you're filtering very inefficiently at 40 microns with those type devices. And one of the things that I've noticed in going in and out of plants through these years is a lot of plants have done a really good job installing new, better breathers. But I still see that chrome filler breather cap there.
What I think is funny is you'll see a reservoir top with a nice breather and the cap over here too.
Right.
So, well, eventually air's going through there.
Right.
So what you guys are talking about, when you have a hydraulic reservoir, where you fill the oil, it often will come with this little screw-off cap, and you can pour oil in through a strainer, which is designed to keep big parts, rags, and different things out. And that cap, what a lot of people don't realize is it's a breather also, and it literally has like steel wool in it. So that is an area that there are other adapters, different things you can do that can be replaced. That's kind of invisible to people, to your point, because it just looks like a cap. They don't realize that allows the reservoir to breathe, so there's air coming in and out. Right. Fantastic opportunity to make a really quick, inexpensive improvement. But people don't think about it because it's just on the reservoir.
Right. And there's a lot of devices on the market. There's multiple ways to upgrade that.
And you don't have to use ours.
Right.
I mean, the point is
Just
put something better on there. Put something
do
that's better
something
that's on there.
better. You'll save money in the long run.
One of the top ingression points, air breathing.
Yep.
Absolutely. One of the components that we've spoken about recently is seals. We talked about seals leaking. Pump seals, cylinder seals. What is the most common or some things that causes a seal to leak?
Generally, seals fail due to excessive clearance or excessive pressure. If those two things do not occur and a seal reaches its normal design life, typically they will lose their elasticity over time. But in situations where you have a high degree of contamination, seals cause friction in order to seal. So if you've got enough contamination at the sealing surface, and that seal is an elastometer, I'm kind of proud that I said that without tripping all over my tongue, you can expect it to wear a lot faster than the metal surfaces that it's actually sealing.
You bring up an interesting point. I think there's kind of an analogy if you look at, if you're machining steel, you can machine hardened steel. Sometimes you use a slurry, and what you have is an abrasive mixed with kind of an oil or a paste. What's an interesting thing that I've seen happen is that elastomeric,
Good word.
seal, which is a soft material, on a hardened steel shaft, say a shaft seal, so you've got some type of rubber on a shaft seal. If you get abrasive mixed with oil between that seal and that hardened steel shaft, it will literally wear a groove in that shaft.
Correct.
And the leak will come from that excessive clearance you were talking about.
Right.
And it's just like a machine, like you're machining a part, like you're lapping a component. That particulate will tend to gravitate. It'll settle in areas, and shaft seals are a fantastic place for it to settle. And now you have an abrasive slurry on your shaft and a pump that will literally wear a groove in, and it'll start leaking. Same thing will happen on a cylinder.
My entrance into the fluid power world came working in a hydraulic repair shop, and in that particular shop, we repaired pump cylinders, gearboxes, and it is rare, or it was rare, that I disassembled anything that was sealed with a lip seal that did not have a groove in it. Hardened steel shaft, just like Curtis mentioned, whether it was an O-ring seal or some of the other various elastometers on the market, there was always a groove in the shaft. And most of the shafts that I've had to replace back in those days when I was doing that type of work was because of wearing the seal fit, where a new seal wouldn't work either.
And that once again gets to clean oil. So if those particulates aren't there, they can't accumulate between that seal and that sealing surface and wear it. So the cleaner the oil is, the less likely that is to occur. But it is a fascinating characteristic to see, because you see it over and over again. You have this elastomeric, this rubber seal, that it looks like it wore a groove in a hardened steel part. It didn't. It was just a way of holding a slurry of abrasive material in. And it once again, it's a very expensive failure, but it's easy to address by just getting your oil cleaner.
I had a customer mention this to me once, is why I bring it up, is he was more interested in fixing his seal leaks throughout the entire system and wanted to wait to focus on the contamination levels in the oil. So 500 gallons a week he would top off, no filter. And that's the reason I bring this up, is so we can discuss. There's a direct correlation between your elevated contamination levels. Let's say a servo system, a hydraulic system has servos, and you're operating at an 18, 15, 13 or 19, 17, 15. There's a good chance that you're going to have some problems with components, but you go on seals too. So I bring that up because if a customer does say, I have a lot of leaks and I'm worried about that right now, there may be a correlation. Good chance there's a correlation. Have you had those scenarios?
Well, the thing is, you don't have to fix one at a time.
Exactly.
So putting better filters in, if you're buying filters anyway, that's not capital budget. And fixing seal leaks is part of a normal maintenance budget. So it's not like you're having to go out and you're having to prioritize money or things like that. It's two things that you can be fixing at the same time. You don't have to do one or the other. And you're not spending a lot of money just improving your filters. Now maybe adding an offline system or something, which is pretty much always helpful. But it's not something you have to do necessarily right away. But just fixing the leaks, getting an efficient filter in, and those seals that are failing, those are a leak. So not only is that a cost because they're having to repair them and they're losing oil, but anywhere where oil can get out, dirt can get in.
Correct.
So I don't think it's an either or. I think it's something that can be done together, and they both help each other. So fixing those seals is going to keep dirt out. It's not just keeping oil in, it's keeping dirt out. which is going to keep your oil cleaner, which is going to make your filters last longer. Upgrading your filters are going to get your oil cleaner, which is going to make your seals last longer. So it's something that you do together that's going to have a systemic or overall improvement in the life of the machine.
Exactly, and I do agree with that. And in this one particular situation that I brought up, I encourage the customer to consider filtering new top-off oil first. Let's go ahead and take that step now, since we're adding 500 gallons a week, and then start to address the leaks. It's an education opportunity, and I think that's something that we've danced around the whole time, but what we're saying here is whether it's testing or having an opportunity to get a new customer, it's an education opportunity as well, because we're going to tell them more about the system than just filtration.
Well, that education opportunity is really critical. You have two things that you can do if you're selling filters. There's two ways you can save money. If you're buying, let's say you're buying filters, there's two ways you can save money. And we've talked about them. You can save money by spending less on filters, or you can save money by getting cleaner oil. And that education opportunity, helping somebody understand the things that are costing them money, the things that are impacting, can go a very long way. And that's what's important, is helping them understand how to get from point A to point B. Now, that doesn't touch on the people that think that point A is the way it's supposed to be. It's always this way. And that goes to another story. The story we heard, this was another coworker that told this story, that he had a customer that had gotten to the point where their 3.5 hour pump change, they had it down to 30 minutes. So they were going through pumps, every couple weeks or something like that.
Yes.
And what they had done was they had figured out that this pump change, they could have another pump ready, and they had different things hooked on it. They had this whole setup that enabled them to take a pump out. It was like a modular thing to take one out and put another one in. And they felt like, okay, well, we fixed our problem. We went from 3 hours of downtime per pump failure to 30 minutes of downtime per pump failure. Well, I mean, you talk about an area where you have an opportunity to educate somebody. They thought that was normal. Okay, well, this is the way it should be. We're just really good at this. You don't have to be really good at that. Let's make that pump last longer. And that's where it goes to with education. Somebody coming in who, it's very obvious on the front end, if somebody comes in and sees that and says, well, I can save you money on your filters, as compared to, well, why are they failing? What can we do to help you with that? Yeah, you've gotten good at changing it. That's still a lot of pumps. Let's look at a way to extend the life. And that's what you're talking about with education. Is one of the things sometimes that you have to tell people is the way it is isn't okay. It doesn't have to be that way. Let's start looking at making those last longer. I'd like you to not be good at changing those pumps, because it happens so infrequently you don't remember how to do it. That's where we need to be. And that's how we can bring real value in the marketplace.
Now, the interesting thing about that particular situation is the company that was doing the pump and valve repairs for that particular now customer of ours, their hydraulic repair shop came back 6 months or so later because of the decrease in repair work coming out of this particular sawmill. They came in thinking they'd lost the business. And I guess technically they did lose the business because the business wasn't there, but they were thinking they lost the business to a competitor, when in actuality they lost the business because the components were no longer failing at that rate.
So education obviously is very important, and that's why we talk about it a lot. Absolutely.
We have a distributor that deals. His company is in the fluid power realm, and they deal in a lot of high-end servo and proportional valves. And he routinely tells his customers that he's going to filter the oil. He can either filter it with a really expensive valve, or he can filter it with a relatively inexpensive but high-quality filter. But he's going to remove particles from that fluid.
I'll take option 2.
This has been the HiPro Podcast. For more information on any of our products or services, you can find us on the web at www.hiprofiltration.com. Remember, please lubricate responsibly.